Suppose a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above ground. The distance fallen, S of t in meters after t seconds, is given by S of t is equal to 4.9 t squared. Find the velocity of the ball after 5 seconds. Now, in a problem like this where a function is given to me, I find that it's best for me to start with a variable key so I can kind of get my bearings. So in this case, it says t is measured in seconds. So t will be the number of seconds that the ball has fallen, and it says that s of t is measured in meters. So you could write s or you could write s of t. So that's going to be the distance that the ball has fallen, but specifically measured in meters. So this is a good place to start. It's a variable key. Now let's look at what we're being asked to find. Find the velocity of the ball after 5 seconds. So we do need to have a little bit of background knowledge about velocity. So in general, when we're talking about the average velocity of an object, the average velocity is going to be the change in the object's position divided by the change in time. In other words, the average velocity is going to tell you how fast the object is traveling, but it's also going to give you direction. So in a physics class, many times they'll say velocity is speed plus direction. How fast is the object traveling in addition to the direction of travel? So average velocity is going to be change in position, in this case that's s, divided by the change in time. And I like to go ahead and add the units on here because s is the distance fallen in meters, so the change in s will be measured in meters, and then change in time is measured in seconds. That gives us an overall velocity unit of meters per second, because sometimes the units can really help you figure out the meaning of what you're trying to find. So the velocity is going to be measured in meters per second. Now, because we're being asked to find the velocity right here after 5 seconds, that's just at one specific time, then we're really being asked to find the instantaneous velocity. Now, typically, when we say find the velocity at 5 seconds or after 5 seconds, that's implied to be instantaneous. We don't often use that word instantaneous, but I'm going to use it here because we've discussed an instantaneous rate of change versus an average rate of change in our previous discussions. So it's helpful to see the difference and note that difference here. All right, so we're basically looking for change in position over change in time right at 5 seconds. So this is essentially going to be the slope of the tangent line at t equals 5. So let's get a graphical picture here, and let's go ahead and start by graphing our function s of t. And you could grab your graphing calculator if you wanted to, but I'm going to do a very rough sketch because hopefully we know that the basic shape in this case is this function is a parabola, and it's a parabola that opens up. So I'm not even going to put any tick marks on my graph, but rather just sketch a parabola that's opening up. It also is centered, or rather has the vertex here at 0, 0. So if you can imagine, if I'm at t equals 5, then basically I'm going up to my curve and I'm interested in the slope of the curve at this point. So if I were to draw in that tangent line, I'm trying to find the slope of this tangent line at t equals 5. So the slope of the tangent line in this case will give me the velocity at time 5. Now, I cannot find the slope of this line directly because I only have one point. So we're going to create a secant line and estimate the slope of a secant line. That will get me the average velocity, and then use those secant lines to estimate the slope of the tangent. So to be consistent with our previous videos, let's go ahead and call this point of tangency point P. And for point P, we have an input of 5, and then we have an output, whatever this y value here is. This y value represents the distance that the ball has fallen after 5 seconds. So we could write this as s of 5, or we could actually go ahead and calculate this value by plugging 5 into our function, 4.9 t squared. And if you want to go ahead and do that, you may, because the output here is 122.5. So remember, what this means is that after 5 seconds, the ball has fallen 122.5 meters. That's the distance the ball has fallen. That is not how fast the ball is traveling. That's not the velocity, because that's not the slope. That's simply the output. Now let me mention, in this case, it's okay to leave your coordinate as 5, 122.5, because this value, 122.5, it was exactly this number. This is not rounded. Now, if you ever have a problem where the y value, the output, ends up being a decimal that you're going to have to round, then I encourage you not to round it and actually to go ahead and leave it written as s of 5. We only want to round one time at the very end of our computation, if at all possible. All right, so there's our point of tangency. So now we're going to move a little bit farther away from point P, and we're going to choose a second point, which we'll call point Q. And if we connect P to Q, then we will be creating a secant line. And now we will have 2 points on the secant line, and we'll be able to compute the slope, which is going to be an average velocity. So let's say we're going to go from time equals 5. How about we'll go from 5 to 6 seconds? So if you can imagine graphically, that's, if I were to come down here, let's say we're going to go ahead and compute the average velocity from 5 to 6 seconds. That will be the slope of this secant line, and then we will compute more average velocities to get a good estimate. So moving on, let's go from t equals 5 to t equals 6. So point P is still the point 5, 122.5. And point Q has a time value of 6. So I'm just going to write the output here as S of 6. That's going to be the distance fallen after 6 seconds. So therefore, the average velocity will be the slope of PQ, which will be y minus y, 122.5 minus s of 6, divided by 6 minus 5. And here's where I would want you to pause the video, grab your calculator, and make sure you can do this computation. This should equal 53.9. Now remember, the units on this are going to be meters per second. So the average velocity from 5 to 6 seconds is 53.9 meters per second. Now we'll repeat this computation from t equals 5, but now we want to let point Q get a little bit closer to point P. So looking at your graph, we're moving point Q along the curve, and we're letting point Q get closer and closer to point P, so the x value of point Q is going to change. So maybe instead of going from 5 to 6, maybe we'll go from t equals 5 to t equals 5.5. So point P, the point of tangency, has not changed. It's 5, 122.5. But now point Q is going to be 5.5, s of 5.5. So now my slope of PQ, which is my average velocity, is found by taking 122.5 minus s of 5.5 divided by 5.5 minus 5. So pause, do that computation, and check your answer against mine. And this should give us 51.45 meters per second. So now let's let point Q continue moving down the curve closer and closer to point P. So that X value will change again, or a T value in this case. So from T equals 5, let's get a bit closer. So how about T equals 5.1? So point P is the same, and point Q has moved. So the X value or the T value now is 5.1. So the Y value is S of 5.1. And my slope, Y minus Y divided by X minus X. And then we'll go to our calculator once more and calculate this average rate of change. So from T equals 5 to T equals 5.1, we should now have an average velocity of 49.49 meters per second. So let's pause for a second because let's look at our average velocities and see if there's a trend. We started with 53.9, then we went to 51.45, and now 49.49. So we cannot stop here because right now I can't tell what these values are getting closer to if we're approaching a value, which means we have to continue to get closer to point P. Now that you've written out the computation though 3 times, you don't need to continue writing out the computation. And in fact, I would be comfortable at this point if you went ahead and started organizing these results in a table. So we don't have to write out all of those tedious computations, especially since really you're going to go to your calculator to do those. So we're essentially looking at our time intervals. So our first time interval was from t equals 5 to t equals 6. So I'll just write from 5 to 6 seconds. We're comparing the time interval, and we're comparing that time interval with the average velocity for that time period. And that was found by computing the change in position over the change in time, which graphically represented the slope of the secant line PQ. So I'm really trying to get you to make these connections between the graphical interpretation and the real world interpretation. So from 5 to 6, our average velocity was 53.9. From 5 to 5.5 seconds, it was 51.45. From 5 to 5.1 second, it was 49.49. And we don't see a trend, so we're going to have to make our time interval smaller. So let's go from 5 to 5.01, and again from 5 to 5.001. Pause the video, see if you can get these velocities, and then compare with my answers. So our velocity from 5 to 5.01 should have been 49.049. And for 5 to 5.001, it should have been 49.0049. Now, I believe we can say that we have a trend here, that these average velocities are all approaching, these values look to be approaching 49. So now we can say confidently, it looks like the velocity after 5 seconds is 49 meters per second. To summarize, we could not compute the instantaneous velocity. So we computed a whole bunch of average velocities, and every one of these average velocities represented the slope of a secant line. And then we saw that these slopes look to be approaching 49. Therefore, we can say our velocity, which is the instantaneous rate of change at 5 seconds, is 49 meters per second.